We are shifting to 6.3. We are trying to get ready for a test on Friday. All right, so we're going to spend 2 days on 6.3. We'll have a couple days to review and then a test. Our topic today is to be able to add and subtract rational expressions. To add and subtract rational expressions. When we add terms together, for example, if you had 3x plus 7x, could you put those together? What would it turn into? 10x. So we add the coefficients, right, the 3 and the 7, but we keep the x the same. Does that work for more variables as well? For example, if I had xy squared plus 4xy squared, could I put those two together? Can I add an xy squared? Sorry, I said xy squared and then I wrote the wrong thing. Can I combine xy squareds with xy squareds? Yes. We are going to be doing similar things but with radical expressions instead. Okay? So we are looking for what we call like radicals. Like radicals are radical expressions that have the same index. So we're taking the same kind of root. And they have to have the same radicand. All right? In other words, we are combining x's with x's. We're combining the square root of 2 with other square roots of 2. Okay? The properties of algebra tell us that we can do this. So if you look at our chart here, this says I can take a square root of 2 and add 3 more square roots of 2 to get a total of 4 square roots of 2. So notice the square root of 2 part didn't change, just like our x's didn't change when we added 3x and 7x. It's the front numbers, those coefficients that we're adding together. And a lot of times kids forget that there is a 1 in front of that. If it helps you to write it in, go ahead and do that. It's not wrong to have it in there. Okay? Here we're looking at cube roots of 7 and subtracting 5 cube roots of 7. So 1 minus 5 would give us negative 4 cube roots of 7. And all they're showing on the right-hand side here is that it works for variable expressions as well. Make sure it's the same kind of root and that what's underneath is matching. Okay? So the way we do this, we are simply combining the coefficients. Our formal way of showing that, we have a nth roots of x, we're adding b nth roots of x, we add the a and b together, we still have nth roots of x. Okay, same thing for subtraction. Now, you don't have to put it in parentheses and put the a plus b written down like that, you can simply add them in your head. Okay? The one thing I do want to caution you of, it says combining radical expressions is different from adding them. The sum of 2 real numbers is a real number. So technically we can add the square root of 2 and the square root of 3 together. We can't physically put them together because they are not like radicals. But we can convert them to decimals and take the square root of 2's decimal and add the square root of 3 decimal to get an approximation for it. What is wrong to do is to actually add those radicands. The 2 and 3 we cannot put together and say that's the square root of 5. All right, and we're showing you that here. We do not get the same decimal out. Okay, so I can add a square root of 3 and a square root of 2 and get an approximate answer as a decimal, but I can't combine them into one piece. Does that make sense? Okay. All right, so at your tables, I want you to look through the first 3 here and decide, can we put any of these together? Can we combine those terms? All right, so what did your groups come up with? Can we add any of these together? Can we combine them? The first one we can? All right. We have the same kind of root. We have square roots of 5x. So the first one says I have 3 of them. We're subtracting 2. How many do I have left? I have 1. Now I can write that as 1 square root of 5x, or I can simply write it as the square root of 5x. That implies we have 1 of them. Okay, either one's fine. Why can't we combine the second ones? There's a couple reasons.
Different numbers in the square roots and also different x's.
Okay, so we have a square root of 7, square root of 5. They don't match, right? So right away, we can't put them together. Even if those had matched, when we look at this, we have different pieces there. So you're really looking at everything after the coefficient has to match in order to combine them. Okay? So for this, you're just going to say can't combine. And for the third one, what was our reason? Different types of roots. We've got a cube root here. We've got a fifth root here. So can't combine. All right. I'm going to pause the recording. I want you guys to try the next 3 and then check in with the people at your table. All right. Can we combine the first one? No? Different types of roots. Cube root 5 and a square root of 5. Okay. Okay, I shouldn't try to write so fast. All right, second one. Can we put that together? Into what? Good. And the third one. Can we put those together? Yes. When we put it together, we're going to have what kind of thing? What's the radical part? Fifth roots of 3x squared, right? That's the piece that matches. So we have 17. We're subtracting 15. We would have 2 of them. Make sense? Okay. Our next question. We have a picture here. It says it's a stained glass window, and it says the side of each small square is 5 inches. So if you just take one of these little squares, we are saying that's 5 by 5. Okay? The question is asking us to find the perimeter of the window to the nearest tenth of an inch. Okay? If we take that little square and draw it down here, I know it's outside of the stained glass window, but can you see how that would continue the pattern? So when we look at the perimeter, we're trying to add up all those pieces on the outside. Each of these pieces is the same as this one, correct? And in terms of that square, what would we call that segment? What's that segment called? In terms of the square, it's a diagonal. I'm pulling back some geometry terms here. Okay, the diagonal of a square. Could I take away 2 of these sides and say that is the hypotenuse of that triangle? Since it's a square, we know we have a right triangle. We okay with that? All right. So we have a triangle. The sides are how big? 5 inches. Okay. How do we find this side? All right, Pythagorean theorem, good. A squared plus b squared equals c squared. What are my a's and b's in this case? They're both 5s. So 5 squared would be 25. Same with b squared. Adding them up, we have 50 equals c squared. So what would c be, the hypotenuse? What would we have to do? We have to square root it. So we get the square root of 50, but we could break that down into what? 25 and 2, which would give us 5 root 2. Yes? So in this case, our dimension here is 5 root 2 inches. So the diagonal of each of those squares is 5 root 2. Did you guys remember that from geometry? Because if we take a diagonal of a square, we've created an isosceles triangle, right? The 2 sides are the same. In any kind of isosceles triangle, your hypotenuse is going to be the side length times root 2. That's always the case. So if you recognize that and went right to saying if my sides are 5, my diagonal is 5 root 2, that's fine. You can skip all the Pythagorean theorem stuff. All right, so now let's go back and look at what we're finding. We now know that this length is 5 root 2 inches. Can we now find the perimeter? How many of those little segments make up the perimeter? We've got 3 on this side. We've got 2 on this side. So 5 gets us halfway around. We'd have 10 all the way around. Okay. So the perimeter is 10 diagonals, which means we have 50 square root of 2 inches. But they didn't ask for that because you rarely go around and tell somebody the perimeter of your square is 50 root 2 inches. We convert it to a decimal. They asked us to round to the nearest tenth. So grab your calculators. What is 50 root 2 to the nearest tenth? Anybody?
70.7.
Thank you. You should get in the habit of including units when they're given to you. So we would say 70.7 inches. Okay? Questions on that? All right, looking back at the ones that we were adding. One sec. All right, looking back at the types that we've been adding together, when the radical part didn't match, we said we can't combine them, correct? We have only looked at ones where the radical has been simplified as far as it can go. If you look at our next example, we are being asked to add the square root of 12 plus the square root of 75 minus the square root of 3. Notice the directions say simplify before you try to add and subtract. If there are perfect squares or perfect cubes, whatever kind of root you're taking, inside as a factor, you have to pull them out first. Then you can compare and say, can I put these together or not? Okay? So looking at our first one here, we have the square root of 12, the square root of 75, and the square root of 3. What can I do with a 12 to break that down? 4 times 3, square root of 4 is 2. So the square root of 12 is really the same as 2 root 3. Okay? What can we do with a 75? All right. So we end up with 5 root 3. Now if you look at what you have, 2 root 3 plus 5 root 3 minus 1 root 3. Can we put those together? Yes, because now they do match. So don't ever say you can't simplify something until you look to see if each of those radical pieces are in their simplest form. So 2 root 3 plus 5 root 3 would be 7 of them. We're taking away 1. We should have 6 root 3 left. Okay? I'm going to pause the recording. I want you guys to try the next one. All right, one suggestion I have for you when you're trying to simplify things, especially if the numbers get to be larger than you're used to, or you're trying to take the type of root and you don't know all the perfect ones, start with the smallest one. Okay, so I'm going to look at this and start with this 16. I want to split it into 2 cube roots. What's a perfect cube in 16? So it would be 8 and 2. So this would reduce down to 2 cube roots of 2. Okay? Now, using that idea, when I try to split these off, if I can combine these together, they all have to have a cube root of 2 as the leftover piece, right? So does 2 go into 54? 27 times, and 27 is perfect. All right, so this becomes 3 cube roots of 2. Does 2 go into 250? All right, and that gives me a perfect cube again. So by starting with the smaller one, it gives you kind of a hint of what you might be looking for. It's not a guarantee that it will always work. I could give you 4 or 5 different radical expressions and say, simplify this, and some of them you might be able to combine together and some you might not. Okay, but it's a good way to start if you aren't sure what kind of perfect one you're looking for. All right, combining these now, we have 5 plus 3, that's 8. Subtracting 2, we should have 6 cube roots of 2. We good with that? All right. The last part that we're going to look at today, we're still going to be combining like terms, like radicals, but we need to do a little multiplying first. Okay, remember foiling technique? When you have 2 terms times 2 terms? So we're going to use that idea. For this first one, I'm going to write out all the little steps. After you see what I'm doing, you can take some shortcuts. When I do first, I have to do 5 times 4. When I do outsides, I'm going to take 4 times 4 root 2. Insides, I'm taking 5 times 2 root 2. And last, I'm taking a 2 root 2 times a 4 root 2. Okay, so I'm putting my pieces together, simplifying them now. 5 times 4 is 20. And most of you would have done that in your head and not written it as 5 times 4. That's fine. The radical parts. We are multiplying a 4 times a 4 root 2. You can multiply numbers that are both outside. You can multiply together numbers that are both inside, as long as the radical part, the root, is the same kind of root. So for this one, I can combine this and make this a 16 root 2, multiplying the 4 times 4. The next one, 5 times 2 root 2 becomes 10 root 2s. And our last one, again, you can multiply 2 numbers if they are both outside. You can multiply 2 numbers if they are both inside. So I can multiply the 2 and the 4 to get an 8. I can multiply the root 2 times the root 2 to get a root 4, which is actually just a 2. 2 times 4 makes this 16. Okay? So I've done the FOIL part of FOIL. Now we want to look for any like terms that we can combine. So the 20 here and the 16, can we put those together? So we end up with 36. Can we combine the 2 radical parts? Do those match? Okay, they're both root 2s, so we combine them as 26 root 2. Okay, let's try one more. First terms first, 3 times 5. 15. What do we get for outsides? I'll tell you the common mistake would be to say that's the square root of 21. The 3 is outside of a square root symbol, the 7 is inside. You cannot multiply those together and make a 21. You can write it as 3 root 7. What you're really doing is 3 times the 1 that's in front. Okay? What do we get for insides? What do we get for insides? Good. And then last, common mistake here is for students to say 0. But if you say 0, you're adding them. It's asking me to multiply them. Negative times positive is going to be negative. 1 root 7 times another root 7 becomes root 49, which is 7. All right. Combining like terms, what do we get? What did you say? Okay, combining these, we would have negative 2 root 7. Can we combine the other 2 pieces? All right, so we have 8 minus 2 root 7. All right, one problem left for today. Go ahead and try that one with your groups. All right, looks like most of you've got this one. The 2 times 3 would be 6. Outsides would give us a 12 root 5. Insides, we should have 4 root 5. And last, if we take the 2 times 4, we get 8. We have a root 5 times a root 5, which is the square root of 25, which is 5. 8 times 5 would be 40. Combining like terms now, the 40 and the 6 can be put together and our root 5 pieces. We have 12 plus 4, we'd have 16 root 5. Okay? All right, so the two things that I need you guys to do, there's a formative quiz in Schoology. It's labeled 61-62. 6 questions. It shouldn't take you very long. Go ahead and do that first. When you finish that, go ahead and work on the 6-3A book assignment.